按这个结束之后的。我一直超肥。哦，他的这个这么多辛苦，但现在到我这里来，只是在找你帮我写详情。这里有这个。
这样吗？ Sorry. Yeah. Yeah. Sure. Yeah.
Okay, good afternoon, and welcome to today's joint colloquium. And it's my great pleasure to introduce Professor Yipeng Jing from Shanghai Jiao University. So Yipeng is a very world-leading expert on cosmology and astrophysics, and also he's a very top of the astronomical society in China. And let me introduce his academic history briefly. So Yipeng got a PhD degree in 1992 at CCMS in Trieste, in Italy. And then he worked as a postdoc in University of Arizona in the United States, and MPA at Germany, and University of Tokyo in Japan. And then he moved to Shanghai Astronomical Observatory in 2000 as a professor. And then in 2012, he moved to the current position in Shanghai Jiao University, and as a dean of the School of Physics and Astronomy. It's a very big department. He's a dean of this school. And 2015, actually, he got received the honor of the Academician of Chinese Academy of Science. It's the highest honor of China. And also, he's currently the president of the Chinese Astronomical Society. So literally, he's the very top of the society. So Yipeng did a very pioneering work around 1990s and 2000 on galaxy formation and cosmology. He did a structural modeling of the dark matter halos for the first time, and also if you are a cosmologist, everybody measure the path spectrum, and actually he made a method to correct for the aliasing effect. Without using his method, you can't measure the path spectrum correctly. So this is very important contribution. And also he's very active, still very active in science, and he's working on a very hot topic. Like he give us a talk today, and so the title is like a measurement of the Milky Way mass in cosmic constant. So please welcome him first.
Okay, so thank you, Captain, for the introduction. And so it's my pleasure to be in Taiwan University. Actually, I think this is the third time. And in the last two times, so I think we had a very busy schedule for meetings, and I had not chance to visit the campus. And yesterday was was a good opportunity. And in the morning yesterday, so I walked through all the campus, and it's really good to visit here. So so today, so I'm talking about the measurement of Milky Way's mass, and so this is a very fundamental question or fundamental quantity in astrophysics. So first of all, so we know we are living in Milky Way, right? So Sun is in the Milky Way. And around the Milky Way, there are dark matter halos. Okay, so later I will talk a little bit more about cosmology. So this is what we understand, that around our Milky Way, there are dark matter halos. And so certainly, so because we are living there, so we want to know how much dark matter there is, right? And certainly in science, so I think how much dark matter is related to some fundamental questions, say galaxy formation, because galaxy formation is shaped by dark matter, by the force of dark matter. And certainly, how much dark matter mass is related to a typical, spiral galaxy is a fundamental connection, okay, in galaxy formation. And also, so we know, cosmology. Usually, so we say that CDM, so-called dark matter dominant universe, is a good, scenario for cosmology. And there are several problems, so-called too big to fail problem, or too many satellites in the theory. So whether there are problems or not is also related to the mass of Milky Way. If you change the mass, so sometimes the problem just appears, or much more easier to solve. So this is in cosmology. And certainly also particle physics, of course, so we want to measure dark matter particle. And how much you would expect is also related to the local density of the dark matter around here. It's also related to the total mass of the Milky Way. So from all these, so this is a very fundamental pumpkin. However, this is the current situation. Actually, there are many ways to measure the Milky Way. Okay. Say, so this is for different categories. So this is so-called from the escaping velocity of high velocity stars, or the motion of layer 1 satellite galaxy, or from local rotation curve measures, or from spherical Jing's equation and its distribution function I will explain later, of stars, usually from stars. And there are streams, the modeling of streams, and the motion of 2 local groups, and also as a so-called according to the amount of baryons, so we estimate how much dark matter there is. So there are many. So I think I have no time to explain each one. And there are, I just advertise, so there will be an excellent review. It will appear in SCPMA. So this is a Chinese journal in physics and mathematics, mechanics and astronomy. So Yipeng will publish quite soon about this. So he did a very excellent review. Okay, so I will not explain each method. So I would just say, so how we can make a good or precise measurement for Milky Way mass. So in principle, how can we, measure it? Okay. So we always, measure the Milky Way mass through its gravity, okay, or from the gravity, its gravity effect, gravitational effect, okay. So usually we model the kinematics of some traces, say stars, okay, say stars. And so why there are so many uncertainties? Mainly because, so I think would be 2 points. So one is usually we can only have very limited range of the trajectory we can model, okay? Especially, from stars, we can only measure stars up to almost 50 kilopascal. So the radius of our Milky Way is about 300 kilopascal. So this means so we can only measure about 1/6 of the distance. So we can only measure, quite local, regions. So this is the one. Okay, this is one, and also another limitation is that we can only use phase-space information, not follow the trajectory. Okay, trajectory. So this means that we cannot do, even right now, you cannot do the multiple time, follow-up of trajectories. Yeah, it's very, very difficult. Yeah. So the key uncertainty actually is the link of the phase space information with the potential wear. So if we know the the theory, and then you can measure it very, very accurately, I think, from observation. But if you don't know much about this connection, or you make some assumptions, then you will get uncertainty. Okay, so this is a long list of uh, the limitations of each method. Okay, so this is long, but certainly this is just my own opinion. So in some categories, such as high velocity stars, even halo stars, actually the origin of these traces are not well understood. So this means the physics. Its origin not well understood. And sometimes you use Jing's equation. In this case, so you have to assume the form of velocity anisotropy, velocity dispersion anisotropy. So this is something we don't know in theory. Okay, we don't know in theory, and it's very, very difficult to make observations. And also, from local, you can measure the local rotation curve very accurately, but then you can measure the mass within the local radius. But when you want to infer the mass of a whole halo, then you have to extrapolate. And in this case, there are lots of uncertainty there. And so also in many measurements, it's difficult to incorporate the uncertainties of promotion, say large errors. Yeah, it's very difficult to include the measurement errors and observational incompleteness. You can only measure some stars in some region, some direction, some region, and then there are incompleteness in observation. And certainly, there are also problems with say potential wear relation. Okay, you have in many cases, so they make some analytical potential wear. But in our opinion, so this is also could be also the problem. Yeah, so there are many. Actually, you can, if you want to list, there are many more set of programs. Okay, so we chose one, new tracer. So it's satellite. Yeah. Certainly, some people already use the satellites to measure mass, but in many cases, they still limit. They have limited some. They only use. They only use layer 1, and in some cases they use the analytical potential wear, and also many of them have not included in their analysis. Okay, so we are considering satellites of Milky Way, and this is our Milky Way, and around there are many so-called satellites. All satellites are very likely within the halo, so it's embedded in halo. Okay, and so this is my argument. So why we want to use satellites? So we think that the origin of this satellite is well understood. I will explain in cosmological content, and then we can model this population. Therefore, we will have very accurate phase space distribution and its relation to the host potential. So because we know in the cosmological context. And also we have developed another advantage is we can measure this satellite to nearly the halo boundary. So this is, I think, so it's here, so quite far away. So it's almost in the boundary. So you can, okay, so we can measure them to almost the halo boundary. So we can weigh sample the Milky Way potential. And in addition, I will show that we can also include the measurement errors and also observational incompleteness. So in this way, so in principle, we can overcome most of the shortcomings, almost all shortcomings in the measurement. Okay. So a little bit about cosmology. Okay. In the last 20 years or a little bit more, so we have many achievements in cosmology. So this is really the transfer of astronomy, and people established from various observations, from supernova observations, large-scale structure observations, cosmic background, microwave background observations, or from different kind of observations, we have established so-called concordance cosmology. Okay? And with the amount of dark matter, amount of dark energy, and with about 5% baryons. So it's already so I will not go to much details, and I think many of you already heard of this. If you want to have precise value of parameters, so we know from such observations, we already know quite many of these parameters. Okay, but on the other hand, especially from the observation of large-scale structures, we have established so-called paradigm of hierarchical structure formation. And here, I think the main property is the linear Paul spectrum, And so this Paul spectrum is measured from the structure of various size, and this spectrum actually very, very close to the prediction of cold dark matter scenario. So this is the prediction of cold dark matter scenario, and this is the measurement. So this means we have established also the structure formation, and in this paradigm, structures are formed from small structure to large structure. So it's called the hierarchical structure formation. Okay. Okay. So in this scenario, actually there are structures you will expect, so which are distributed in filaments. Okay, in filaments, and along this vertex of filament, there are here so big clusters, and of course, even on small filament, there are also maybe groups, even bigger galaxies. Okay, and within the halo, such as this halo, if you zoom in, and you will see many subhalos here. So many subhalos here. Okay. And it is possible to make the connection of this halos, subhalos with halos. Okay. And so this is just, I think, a much better presentation of hierarchical structure formation. And this is the so-called dark matter halo. And if you trace back, and you will see, so there are in early time, there are many small halos. They are merging to big halos, and they are merging together with big halos. Okay. So this is just a hierarchical, structure formation, and then you would expect, halos, merging. And early time, so in small head, even at early time, so in the center of the halo, there could be galaxies formed. Of course, these two merge, and there could be another one here and another one here. So this is it's incomplete presentation here, and there could be one and another one here. And then if they getting together, and you will have central galaxy and satellite galaxies. So corresponding to our Milky Way, then this is our Milky Way, and there are satellites around. Okay, so we know very well. So all these satellites are connected to early stage. So they're early, in early history. So overall, we know their connections and also their dynamics, both their dynamics and their formation history. Okay, and other two things. So it's important for modeling. So one is the so-called density distribution of this halo. Okay, so in terms of the radial density distribution, it found that all halos at different mass is followed by simple density profile, so-called Navarro-Frank-White profile, and there are only two parameters. One is the so-called scale radius, and one called the scale density, which is at the density at scale radius. And the scale density is related to the halo mass. Actually, you can find how much they are related to halo mass. So this is the quantity, so you can see that there is only two parameters. One is scale radius, and one is the halo mass. One is halo mass. And with this relation, you will expect so the phase space parameters, say radius, also the position and the velocity can be scaled by scale radius and scale velocity. So this is just the definition here. So there is some self-similar relation of the distribution function. Okay, distribution function you would expect. Okay, so this is one. And another one is also the distribution of halos. Okay, so even this is the density. Sorry. So this is density, mass density distribution. And in another paper by Jiaxin Han et al., and they found that the distribution of halos actually is also universal in space and also in the density. In density or in mass function and in space, it's self-similar. Okay. Oh yeah, actually So it's good question. Yeah. So the concentration is the ratio of the radius of the halo to RS. And so this is equivalent if you use concentration or you use RS. Yeah, because there are only, I say, two parameters. One is halo mass, one is RS. So these are two parameters. Or you can say mass and the C. Yeah, so these two are equivalent. Yeah. Yeah. Okay. Yeah. And so up to now, I'm for the halos, and now we want to connect some halos with satellite. So this is a luminous galaxy, and there is a relation. So it's the stellar mass of satellite to the halo mass. It's a function of halo mass, and we know so there is a relation from large scale structures, and we know. So in this case, then we can connect, the satellite luminosity to satellite halo, subhalo mass. So in all, if you're putting all this together, then we have complete, description for the satellite, okay, of the origin of satellites. Okay, so why now it's good time for this? Because there are recent observations. So let me talk about the recent observations. Actually, so this is a good opportunity now because there are many large photometric surveys like dark energy survey earlier. So it's pan-star observations, and in future we have LSST observations. So we have many different kind of observations which have discovered more and more satellites. Okay, fainter and fainter, more and more satellites. And also, there are good opportunities of good Gaia satellite. This is man-made satellite, not not satellite galaxy, but a man-made satellite and satellite telescope. And from this satellite telescope, we can measure so-called proper motion of satellite galaxies. So in astronomy, it's quite easy to measure accurately the position in sky. And also it's quite, in my opinion, so it's still quite easy to get their velocity, radial velocity from their spectrum. So you just measure their spectrum, and then from Doppler effect, so then you measure their radial velocity. But one thing is very difficult is so-called the velocity perpendicular to your line of sight. It's extremely the change of the position on sky, and it's very, very slow, on sky change is very, very slow. So you have to make a very, very precise measurement to get this velocity. And only recently, so there are many good samples from Gaia proper motion measurements and in this region. Okay, so this also the reason so why we should consider this. 5 years later or 3 years later, the sample is much smaller, maybe only 8 satellites, now 30 satellites. So this is a tremendous increase of the sample, and this means a good opportunity for measuring. Okay. Now, see how to model this. So this is then the next stage. So this is we should how to model the phase space distribution of satellites. Okay. So certainly, literally, so the phase space information is R and V. So this is the 6D information, right? Of course, once we have this observation, then we have 6D information. But if you use coordinate and velocity, then usually sampling is very, very sparse, right? Very, very sparse. And if you have only 30 tracers, it's difficult to express completely. But we know if the potential is approximately spherical, then you can use energy and angular moment to to approximate. Then you should then if you use only just two parameters, then the phase space sampling will be much better. So so this is the reason. So we use this two from our paper, 2 years ago. Okay. So the method actually is quite simple. So in this way, the method is simple. So we just use, a sample of dynamical tracers. Here is the bright satellites, which have purple motion. Right? So then we construct the phase space distribution function from high resolution cosmological simulations, and we plant satellites into subhalos and get the phase space distribution of satellites, and compare model phase space distribution with observation, and using statistical way, so-called either maximum likelihood estimate or Bayesian estimate. So you can use statistical way to infer the mass. Okay, mass. So this is the way we are doing. Okay. So in more detail, so I would say, so this is the function in the space of energy and angular momentum. You can measure, it's distribution function. But if you relate with the distribution function